I'm a quantum physicist, theoretical quantum physicist in the School of Physics and Astronomy, for those who don't know me. And I met Rosemary, gosh, it was probably about 9 years ago now, so first time, soon after I arrived at Monash. And we quickly discovered that we had sort of a shared love of few-body physics, of few-body problems, although albeit from different sides. I was interested in the quantum side and Rosemary from the classical side, and we kept saying we should have a discussion. And, well, here I am, finally, having that discussion, or at least starting that discussion. So I'm going to give you a fairly high-level, sort of brief kind of picture of some particular aspect of the three-body problem that I like. And I'm not the only one, I think, who thinks the three-body problem is important. There's a very best-selling novel that many of you may have come across, also about the three-body problem. Have you come across this, Rosie? Yes.
It's a bit violent.
Yeah, okay, so maybe not but it's even being now apparently converted into a Netflix series, was what I heard. So obviously, even from the creators of Games of Thrones, so maybe that makes sense with the violence aspect, yes. But anyway, nonetheless, it underlines how this is a popular problem, not just from my perspective and our perspective. Okay, so this obviously was more focusing on the classical sort of celestial problem. So what about the quantum mechanical version? So what I'm imagining here is we once again take three objects, three quantum particles now, and we imagine they have attractive interactions between them. So in this case, they have short-range attractive interactions. And what's interesting in this case, well, firstly, what I found was already kind of remarkable is just how much, at least on the surface, how much simpler it appears. There's no chaotic behavior. Okay, so it's a linear system. There's no, so unlike the three-body problem that you discussed, Rosemary, there's no sort of dependence on initial conditions like that. It's even sort of nicely analytically solvable in special cases. Now you might think, does this mean it's boring? And of course, if I'm standing here, hopefully it's not the case. But the other thing I wanted to emphasize at this point is this is even if it's a very simple problem to state, it's something that can be realized in a range of systems. It can be realized with atoms, even nucleons, and even magnets. It's been claimed that even the excitations in a magnet can actually realize this kind of problem. So it's something that's really pops up in many different quantum settings. So let me sort of think a little bit more about how does this problem behave. So what I wanted to think about, and this is coming back to even this idea of resonance. Okay, so we imagine we have now the simpler case of three identical particles. I'm going to specifically think of them as bosonic particles. You remember there's bosons and fermions. Bosons are the ones that like to cluster together. Unlike fermions, which like electrons, they don't like to they don't like to sit on top of each other. Bosons are the kind of sociable ones. So we have bosonic particles. We have short-range resonant interactions now. So what that means now, it's you think about a resonant interaction. It's really the strongest type of interaction that one can have in quantum mechanics, and it's really arising from the fact that you're close to forming a bound object of two of these particles, right? So the resonance derives from the fact that you're nearly going to form like this bound two particle object that almost going to bind. Okay, so now how do we think about this? So it turns out, okay, so you can convert this into a much more mathematically simpler problem. So if you think about instead of trying to analyze all the coordinates individually, you can take what's called a hyperradius, which is really just a summing up all the coordinates, of these, the radius. If you're thinking of some origin, summing up all the distances of these particles, all the sum squared, the radius, and now you actually have a problem that you can write just in terms of this radius. A simpler problem in this case, and so you can now think about reduce it to a problem of a particle sitting in a potential. As a function of this radius, okay? Now it turns out it's interesting. So this is it's a textbook quantum problem. It's appeared in a old classic textbook by Landau and Lifshitz back in the 1950s, 1958. And what's interesting, this at first sight looks to be a very kind of slightly pathological problem. It's basically this 1 over r squared potential problem. The problem of a quantum particle sitting in a potential of this form. And what you quickly realize is that in this case, unlike in, say, when you solve a problem of, say, the hydrogen atom, you get these nice little energy, well-defined energy levels. In this case, with this particular 1 over r squared potential, not 1 over r, you end up with particles wanting to, collapse towards the center. So you have the lowest and the ground state being essentially, negative infinity. So this was regarded as initially a very, a curiosity in these textbooks. There's this classic quote from this textbook, which is like, oh, this is a very, it's useful to consider this model, but of course it has no direct physical meaning, and this looking at this potential here. But as we know, it turns out this actually does appear in nature. So it's one of these curious things where something that looks, so simple, like relatively simple problem, and it can actually, appear in the three-body problem. So then coming back to the fact that this is a slightly sort of pathological problem at first sight, what it turns out is that this pathology, if you like, gives rise to very rich and exotic physics in this few-body setting. So in particular, it really defines what kind of three-body binding that you have, what kind of bound states that you have. And so essentially what you need to do, naturally the way you want to kind of try and fix this problem is you say, well, I'm going to just put in a boundary at short distances. Okay, if I put in this boundary, let's see what happens. What kind of states do I have? Okay, now I no longer allow them to fall to the center. I'm going to stop them at some certain point. What do I get? Now, this brings me to this really kind of nice, kind of all these very nice bound trimer states, which were first sort of recognized by Vitaly Efimov back in 1970. Hence, they're called Efimov trimers, and they're known as they're often referred to as what's called a type of Borromean state. Okay, what is a Borromean state? That's really saying you have an unusual situation where you can have three particles binding together to form this trimer, this three-body state, but the two particles cannot bind. Okay, and this is really nicely illustrated by these Borromean rings. You see how you can have like two, if you take one of these rings away, they fall apart, right? So you need these, these overlapping rings. You need to have all three of them to actually form this bound kind of ring structure. And this is a sort of very nice analogy that people have used to really to describe this concept of this Borromean state, this three-body state. And this is something that actually it was initially, like I said, it was predicted in the back in the 1970s, and it was observed for the first time in a gas of cesium atoms in 2006. And I should say that this idea of the Borromean kind of rings is a very old concept. This is taken from an image of a church in Florence, the Santa Croce, where you see once again this very nice kind of Borromean ring structure. So you have this nice kind of I kind of like how you have very kind of like a very nice visual analogy of what I think is a kind of very interesting mathematics in this case. But wait, there's even more stuff. There's even more to this story, apart from this kind of idea of the Borromean state. Turns out there's actually an infinite number of such trimer states. So remember, we had our potential and we imposed some boundary, and it turns out so you can have your smallest state that's set by this boundary. You have your smallest trimer, but you have an infinite series of trimers that are all kind of related, sort of to the original one, just by a scaling factor. So you can scale this by up here, or scale it larger and larger and larger, and you can keep making it. In principle, okay, if you had an infinite kind of box or system, you could have an infinite number of these kind of bound states. So it's often likened to the series of Russian dolls, where you kind of make, okay, this is obviously of a particular, each doll is related to each other by a little, by a scaling. You scale it down further and further. So in this case, you have an infinite number of them. And this is, I noticed initially I wasn't going to mention this, but I noticed in your slide, Rosemary, you mentioned limit cycles. So this is an example of a type of limit cycle where you can kind of, in that case, what you can vary is, say, if you vary the size of the lowest trimer, if you keep varying that, you essentially, recover, each time you go through this scaling, as you vary by that scale, you recover the same series again, so periodically. So it's quite a nice kind of physics here. Anyway, so that's kind of like the kind of essence of this problem. And okay, finally, in sort of my last thing, so I've got a shorter talk, I think, is what I wanted to mention is that where we're fitting into this is that we're interested in trying to understand how this kind of very profound kind of properties of this three-body problem might feature beyond the three-body problem, say in the case of many quantum particles. How does this kind of Efimov effect, how might this manifest when you have many? And one particular sort of simple situation we've been looking at is where you say we have like effectively what's called the quantum impurity problem, where you can think of painting one of the particles, say a different color, say red, and you have a sea of other types of particles, so like say blue particles, and we've been looking at how does this three-body problem affect this problem, and what we've found, for instance, is that you can get, like if you're looking at things like the energy of this system, you can have actually a universal physics, like a universal dependence on this Efimov scale. So, for instance, the scale of the smallest, scale of your smallest trimer, for instance. Or another kind of interesting feature is that you can see that just by scaling the density, like the number of particles, or changing the interparticle spacing, the spacing between particles, you can tune in and out between different. Every time you have this a trimer, size of a trimer that sort of overlaps with the interparticle spacing, you get kind of the similar physics, the same kind of physics emerging as you do that. So anyway, so I think that's basically what I want to share with you today, and I hope I've at least convinced you that there's lots of stuff that we have more to talk about, and it's an interesting problem.
Yeah, thank you.
Yeah, thank you.